Terms and substitution. Constants, CD and so on, and variables x, y, z and so on are called terms. Characteristic of terms is that they have a value if we fix a model and an assignment. In logic, sentences have a truth value which is 0 or 1, just two possibilities, but terms can have any element of the model as their value. The value Tm of S of a term T in a model M under the assignment S is defined as follows. If T is a constant C, then Tm of S is simply the value of the constant in M. So that means that in this case the value is independent of the assignment. On the other hand, if T is a variable x, then Tm of S is simply Sx. It is the value of the variable x in the assignment S. If we had function symbols, as we do in the end of the course, although not yet, such as plus, minus and times, there would be more terms, such as x plus y, x times y, x plus y times x minus y, x times x, etc. Indeed, we could form polynomials. Bound variables can be changed within certain limits. A bound variable can be changed to another without changing the meaning of the formula. For example, if you change x to z in for all x r0 xy, the meaning does not change because the following are equivalent. S satisfies for all x r0 xy in M, and S satisfies for all z r0 zy in M. The meaning of both of these is that the set of A in M such that the pair ASY is in R0 of M is the whole set M, and neither X nor Z plays any role in this. This is like in algebra. Sigma I goes from 1 to 5 AI is the same as sigma j goes from 1 to 5 aj. Both are equal to a1 plus a2 plus a3 plus a4 plus a5. But one has to be careful when changing a bound variable. If you change x to y in for all x r0 xy, the meaning does change. The following are not equivalent in general. S satisfies for all x r0 xy in M, and S satisfies for all y r0 yy in M. The meaning of the former is that the set of A in M such that the pair ASY is in R0 M is the entire set M, while the meaning of the latter is that the set of A in M such that the pair AA is in R0 M is M. This is like sigma I goes from 1 to 5 AIK is not the same as sigma k goes from 1 to 5 AKK. The former is A1k plus A2k plus A3k plus A4k plus A5k, but the latter is A11 plus A22 plus A33 plus A44 plus A55. The general rule is, when a bound variable is changed to another, no free occurrence of any variable should become bound. There is an easy way to accomplish this. If a bound variable is changed to a completely new variable, no free occurrence of any variable can become bound. The concept of, quote, free for, unquote. We shall now dig a little deeper into the question, when can we substitute a variable to another variable in a formula? When we deal with simple, short formulas, the matter is easy and can be decided by common sense. But we aim at an exact definition which could be even programmed to a computer. After all, computer manipulation of formulas is nowadays important in industrial applications of logic. A variable x is free for another variable y in a formula A if no free occurrence of y in A becomes a bound occurrence of x if x is substituted for y in A. For example, x is free for y in for all z r0 zy. Substitution yields for all z r0 zx. On the other hand, x is not free for y in for all x r0 xy. Substitution yields for all x r0 xx, and the free occurrence of y in the formula has become a bound occurrence of x. The concept of a variable being free for another variable in a formula can be given also a more exact inductive definition, but we omit it here. We agree as a convention that a constant is always free for any variable in any formula. The reason for this is that if a constant is substituted for a variable, it cannot give rise to a new occurrence of bound variables because a constant is not a variable at all. Substitution is a common feature in mathematics. If we have a polynomial px equals x squared plus 3x plus 1, we can substitute values for x and investigate the arising values of the polynomial. In this case, for example, p0 would be 1, p1 would be 5, and p minus 1 would be whatever, minus 1. Similarly, if we have a formula A with a variable y that has a free occurrence in A, then intuitively A says something about y in each model. For some values of y, the formula is true, depending of course on whether there are other variables that occur free in A, and for some other it is false. If we substitute a constant symbol c in the free occurrences of y in A, then the resulting new formula says something about the value of the constant c. If we substitute a completely new variable w in the free occurrences of y in A, then the resulting formula says something about not anymore y, but the value of w. More exactly, a t/y is a formula obtained from A by substituting the term t for y in every free occurrence of y in A. We never use this notation unless we know that t is free for y in A. Here is a table of results of substitution. P0y. We substitute x for y and we get P0x. Exists z, zey. We substitute x for y and we get ez, zex. Exists z, left parenthesis r0, zy implies for all x r1, x, z, right parenthesis. The formula ax/y is in this case there exists z, left parenthesis r0, zx, implies for all x r1, x, z, right parenthesis. Then the formula there exists z, left parenthesis r0, zy implies for all x r1, xy, right parenthesis. In this case, the substitution of x in free occurrences of y is not allowed, because the last occurrence of y, which is a free occurrence of y in this formula, would become a bound occurrence of x if x was substituted in the free occurrences of y. The key property of substitution is the following substitution lemma. This lemma says, if x is free for y in A, then the following are equivalent. S A/y satisfies A in M, and S A/x satisfies A x/y in M. This lemma is easy to prove by induction on the length or the structure of the formula A, but we omit it here. Note that the real content of this lemma is that there is no difference if we change the value of y in the assignment to A, or if we first replace the free occurrences of y by x and then change the value of x in the assignment. Valid formulas about quantifiers. There are two fundamental valid formulas related to quantifiers. The first is for all y A implies A t/y whenever t is free for y in A. So why is this valid? Suppose M is a model and S is an assignment. Let us suppose S satisfies for all y A in M. Let A be the value of the term t in M under the assignment S. Then S A/y satisfies A in M because all elements satisfy A in M. By the substitution lemma, then S satisfies A t/y in M. So here you see how useful the substitution lemma is. The second fundamental valid formula related to quantifiers is A t/y implies there exists y A whenever again t is free for y in A. So why is this valid? Suppose M is a model and S is an assignment. Let us suppose S satisfies A t/y in M. Let A be the value of the term t in M under the assignment S. Since S satisfies A t/y in M, the substitution lemma gives that S A/y satisfies A in M. Thus, by the truth definition, S satisfies there exists y A in M. Neither of these two fundamental valid formulas is valid if t is not free for y in A. Let us now recap. We need substitution in formulating logical laws concerning quantifiers. In order that substitution goes right, we need the concept of free for.